let's look at other trig functions. I didn't really specifically call sine and cosine the function, but yes, sine and cosine, there are the two functions. And then now we can look at let theta, right, be an angle, any angle. And so here's how we define it. Now, tangent, notationally, tangent, TAN, right, tangent of the angle theta given for here is defined as sine of theta divided by cosine of theta. It's just the way we define it, the way we call it like that. So anytime you're calculating tangent of theta, the way we calculate that, calculate the sine, calculate the cosine, put them in a fraction in this order. That's how you get tangent. Okay? So it's a definition. And then there's another one here, cotangent. And so by the way, tangent right here is short for, this is how we formally say it, tangent, right? That's a short symbol for that. Then we got cotangent, notationally COT, right? We define that as the calculation goes cosine of theta divided by sine of theta. Right? That's how we're defining cotangent. And then that COT, right, is short for cotangent. Right. And then there are two more. And then we will also have a definition, the secant. So SEC is short for secant. Secant of the angle theta is defined as 1 over cosine of theta. That's the definition. And then secant is short for, how we spelling it, secant. And then cosecant, CFC of theta. That is defined as 1 over sine of theta. CFC, short for cosecant. That's how the term goes. Let's look at the first example, direct example. 1. Okay. That's the first example in tangent, the other trig function we're looking at. Alright, so before we proceed, because this is so far just the general instruction of the example, right? But before we proceed, I really need you guys to have that unit circle right by your side again, right? So that it saves you from flipping your pages back and forth again. Right? So look right on your unit circle. Pick an angle for me. Pick pi, right? So with that given one right here, then so with the instruction of the problem, let's calculate tangent of pi. See what I mean? Right? So tangent of pi is, according to the definition that we've had, and that's sine of pi, right? Over cosine of pi. Okay, looking at that right there. Right? So now these are the values that you actually already have direct access to, right? So what's sine of pi quickly? 0. Okay. What's cosine of pi? Thank you. So 0 divided by negative 1? 0. That's how we formally do it. In case that, without the calculator, right? That's how we do it. Now, what about cotangent of pi? And how about, let me write it over here. Cotangent of pi. Okay. The way to calculate, we need cosine of pi divided by sine of pi. You guys with me there? Go ahead and tell me. So cosine is what? Cosine is negative 1, right? And we divide by 0. It's undefined. See what I'm saying now? Actually, I prefer that you guys use the term undefined here because the word doesn't exist. Will not come until like the formal calculus course. It's reserved for a different concept. So anytime you're dividing by a value being a zero, it's an undefined expression. Right? So cotangent of pi is undefined from now on. So what about secant of pi? Okay, so get comfortable with that. Secant is given to be what? Calculated as 1 over cosine, right? Pi. So 1 over -1, right? Which is a -1. We all get that? That's how the process goes. And then when you're taking notes on these problems right here, I hope you guys get the generality of that rather than just copying down the notes like step by step, because this is just how I present the work. But the idea is the access to get to that calculation, right? That's how we're doing it. We take 1 and divide it by the previously known value for cosine of pi, right? See what I'm saying? No? So what about cosecant of pi? Okay. So 1 over sine of pi, which is 1 over 0. Now what can you say about that final? It's undefined.
Wait, isn't it 0?
Divide by 0, so we can't divide by 0, remember?
Okay.
Yeah. That's why earlier we couldn't divide by 0. Yeah. Now when the 0 is on top and something else non-zero in the denominator, that's where you got the 0. Like this case right here. 0 in the numerator divide by something else in the denominator, that's completely 0. But then 0 in the denominator, right, completely, that's, it's that, right? So the answer is undefined. So let's call it part A. So for the later one for here, I'm not even going to bother writing down the steps for here. The steps you guys know it. All I need is now you pick for me an angle, and then you do the calculation. And leave things in exact expression as much as you can. Okay? So pick an angle theta. Pi over 2. So what's the tangent of pi over 2? Undefined. The reason for that, once again, is sine pi over 2 right, over cosine of pi over 2. That's the way we calculate it. So, and this time it's not that important if you write it down anymore. Right? It's just, this is the way we're calculating it. Sine of pi over 2 is a 1, right? And the cosine is a 0. You know what I mean? That's why it's undefined. So what about cotangent? Remember, cotangent is defined as cosine, right? Or sine. Actually, it's pi over 2, sorry. 0. So it's at 0, right? I agree. 0 over 1, right? And I'm writing that down here just for everybody else to see where that thought process come through. And when you're doing this work right here, I hope that you can even go faster than that, right? So what about secant of the angle pi over 2? Reason for that? Secant is 1 over cosine, right? And the angle here is pi over 2. So that's why it's a 1 over 0, leading that to a undefined. That's the reasoning. What about what do you have there for that? 1, right? I agree as well. The reason for that, right? It's 1 over sine pi over 2. That leads to 1 over 1. Right? That. So, like I said, my aim here is just to get you guys fluent, so we don't even have to copy down like the step by step. Because the steps now is just something to present everybody else in case you don't agree with the answers, right? But as far as just the real-time calculation, getting the answer is what matters for these kind of simple, straightforward problems. Yeah. See what I mean? Okay. The only hope is that you don't need to use your calculator yet. That's my only intention with it. And that's my only hope for now, that you can just simply rely on your unit circle.
Pi over 6.
Pi over 6? Tangent of pi over 6, right? Now, allow me just to get in this one a little bit to show you some of the algebra, a little bit, okay? But yes, admit it's the exact same way. It's sine of the angle pi over 6, which we should know the answer pretty instantly, right? Divided by cosine of pi over 6. You guys follow it? Okay? Go ahead and read it out. Sine of pi over 6 is 1/2. I agree. Okay. What about a fraction, right? Over what about cosine of pi over 6?
Root 3 over 2.
Thank you. So we have a pretty lengthy expression like that, right? Pretty complicated looking. A fraction over a fraction. Let's see. So that's where you can quickly do the algebra. So remember from algebra that when you divide a fraction by a fraction, it's the numerator of fractions but multiplied with the reciprocal of the denominator fraction. You guys remember that? Okay. And so I stepped into this particular one right here to show you, to remind some of your algebra with that. And then the 2 got canceled, right? And then here that reduces down to a 1 over square root of 3. You're technically done. You're technically done. But again, the final answer is preferred in the form where you rationalize that denominator. So make sure you multiply the denominator by square root of 3, and you also multiply the top by square root of 3 again to rationalize that, right? And so now it's square root of 3 over 3. That's how it's done again. So once again, that's hopefully the only one step, the only one problem where I have to show so much reasoning. You can get started on these other guys here. Spend your time doing the cotangent of pi over 6. Okay? And I would prefer that you can spend your time doing secant of pi over 6 and as well as the cosecant of pi over 6. Get me the answer in the final exact answer like this, right? Instead of the decimal. I'm very bad at the decimal, so if you tell me the decimal, I have no way to confirm that. All right, cotangent of pi over 6. 3. I agree. Now, the reason for that, so cotangent is cosine of pi over 6, right? Divided by sine of pi over 6. That's the reason, right? And then cosine of pi over 6 in turn equals what? It's a square root of 3 over 2, right? And now sine over 6, so we got square root of 3 over 2 divided, right, by 1/2, being the sine of pi over 6. You guys know that? And then that's why it leads to, now dividing that fraction, square root of 3 over 2 into the other fraction, we multiply with the reciprocal, 2 over 1. That's why the 2 cancel to end up with that. Right? That's the reason we got it. So what about the secant of pi over 6? How about just write it down like this? 1 over cosine. So what's cosine of pi over 6? Yeah.
I have a guess for the answer, but I'm really not confident. 2 root 3 over 3?
2 root 3 over 3? Okay, I agree. Okay. Yeah. What's the reason for that? Just the word for that, right? 1 over root 3 over 2, I agree. Just like that, right? And then algebraically, we write it as a 1. It's a 1 divided by a fraction, right? So we multiply with the reciprocal, 2 over square root of 3. You get that? Okay. So now that will become 2 over root 3. Yes? And then we rationalize that denominator. Multiply square root of 3 to both top and bottom. Right? And then so it turns into a 2 square root of 3 over 3. Yes, I agree with that. So go ahead and try the last one right there. So go ahead and read that answer of yours.
Is it just 2?
Is it 2? 1 divided by sine of pi over 2, and you find the 6, right? And that's the 1 divided by 1/2. And that's why it goes to 2, right? Because it's 1 times the reciprocal 2 over 1. So we've learned our first fundamental identity. We call it, it's the Pythagorean identity, right? Just the other day. So sine square of theta plus cosine square of theta equals 1. You guys all agree? It's thing that we just picked up with. Not even the other day, just the lecture right before this, right? And so now, it's a known identity. Putting that here in a box, no violations. No way that this can be violated, right? Always true. Pythagorean identity. All right. So now I want you guys to think this way right here. I'm going to rewrite that identity. Sine square of theta plus cosine square of theta equals 1. Okay. So from that identity right here, let's do this. Can we algebraically divide both sides by sine square of theta? I mean, technically we can. Why not? Right? You can always divide both sides of an inequality by any expression, right? As long as the expression is non-zero. Yeah. So I divided both sides of that identity by sine squared. That's just some work I'm doing. So now let's look at the left-hand side right here. The left-hand side, we got two terms in the numerator, right, and one common denominator here. You guys will see that. So we can break it apart into a sine square of theta over a sine square of theta, okay, and plus cosine square of theta over sine square of theta. Okay. And then over here is 1 over sine square of theta. You guys agree on that still? Okay. That will for sure equals 1, right, in the next step, right? We got 1 plus. What do you realize about this? That's right, cotangent square of theta. You guys see that? The reason for that, because cosine square, remember I introduced that notation, right? So when you're writing it like this, it also means you got cosine of theta over sine of theta, all square. You can group it all in one fraction and it's an over all square, right? But hey, cosine over sine, right, is a cotangent. That's why that term right there became this. Right? What about the right-hand side? What do you recognize on the right-hand side? It's a cosecant, right? Square, right? Cosecant square of theta. Because on the right-hand side it was primarily, or originally 1 over sine square of theta. But that means it's 1 over sine theta all square. Right? So that's why it leads down to this. Because this thing right here is a cosecant, right? According to that definition we've just picked up right here. So ladies and gentlemen, all of a sudden we derive another identity right here. It's another version of the way I would see it. It's in one family of the Pythagorean identities now, right? So Pythagorean identity now is not only just one, we got identities right here, right? That's the fundamental one, and then it gave rise to this. See what I mean? Right. So we got another one added into your the list of identities. So maybe it's starting to get, it's going to become beneficial. We can write down, or save for yourself one page of notes just to write down these identities that we're, on our way to derive and keep discovering them. So as far as I've been showing, right, the first one I introduced earlier in the lecture. So we got, as far as the trig identities, right, we got this famously known one, sine square plus cosine square. Okay, so always equals 1. No one can argue about that, right? And then from that, you just now get rise to 1 plus, right, cotangent square. That equals cosecant square of theta. That works too. Right? It's another one, but this one here was born from that other one. So this one right here, put big star on that. This is the fundamental one. Get rise to these guys. See what I mean? Okay. And these are not examples. These are work that I'm showing you. But I hope you learn a lot of algebra techniques from here, so that you can see that sometimes starting with one known inequality, and you can start proving a lot of the other inequalities, and you can also derive your own identity as well. Okay. definitely you gotta stay close with the algebra on these things, okay? And blend it together with our new understanding in terms of sine and cosine. And so back to that known, famously known identity. We roll back to that beginning point. So right from that, I decided earlier to divide both sides by sine, right? Sine squared, right? We can also divide both sides here by cosine squared. Because being an equality, we can divide both sides of an equality by any expression, as long as the expression is non-zero. So instead of dividing both sides of that the identity by the sine squared like earlier, now I just divide it by cosine squared. And so what's good about this? So I'm doing a similar work. I'm breaking this apart, right? Two terms to be separated out like that. So I'm looking at sine squared theta over cosine theta. You guys start recognizing something? And then plus, now this is the common denominator. So we're looking at cosine squared theta over cosine squared theta, right? And then that equals, on the right-hand side is 1 over cosine squared theta. So very similar argument like what we've done earlier. What do you recognize? Well, that goes to 1, right? Of course. That's plus 1. What do you see about that sine squared over cosine squared? It's not only tangent. Tangent squared, right? It's a tangent square of theta. There you go. So tangent square of theta plus 1 equals what? What's on the right-hand side?
Secant squared theta.
That's a secant square theta. That's right. So now all of a sudden you realize, hey, you have just now derived, right? You have just now discovered another Pythagorean identity with them, right? Another identity in that family of Pythagorean identities. Okay, so now I'm going to write it on this list right here. And you can also rearrange the terms a little bit. So more commonly, textbooks writing it as 1 plus tangent squared, right? Like that, equals to secant squared. Very famous. All the algebra that led us to these these fascinating nature of Pythagorean identities. Okay. And there are more. There are still more. I'm going to go back to this fundamental one. Gosh, there are a lot we can do with these. Okay. Right from here, this fundamental Pythagorean identity right here. Can we subtract cosine squared from both sides? Sure, why not? Right? Anytime you have an equality, right, you can always subtract one same expression from both sides. Right? And so, subtracting cosine squared as a choice right now, as a choice, subtracting cosine squared from both sides, what do we end up with? Sine squared on the left-hand side remains, right? Because the cosine squared got canceled away, agreed? And then the right-hand side becomes 1 minus cosine squared later. You have another, surprisingly, it's not too much done. There wasn't too much done, but surprisingly, we can also use this as another rearranged version of that same Pythagorean theorem identity again. Right? So some textbooks also list that as an actual. Some textbooks also list that as an actual identity as well. See? So sine squared can also be understood as 1 minus cosine squared. See, when later on when you guys arrive at a calculus course, you will see that I use this with my students a lot. Okay? So we got the straightforward version, and then we got the rearranged version of the exact same. Okay? And then the other version I was about to say, then think about that. I hope I don't have to derive that anymore. But yes, cosine squared can be rearranged as equal 1, right? But minus the sine squared. Okay? You have another rearranged version of that same exact identity. And with this one in the middle, 1 plus cotangent squared, right? Equals cosecant squared. You can also rearrange by. There are so many different ways actually. So some textbook is doing this. Cotangent square of theta equals cosecant square of theta minus 1. You can also write it that way. So what happened here, you just simply subtract a 1 to the other side. Rearrange that 1 to the other side. Make that a minus. It's another commonly used identity as well. It's a rearranged version of that identity here. And then, the point here is that you guys know how, you guys follow how I derive that, so that hopefully you don't have to memorize too much. Otherwise, at some point in the quarter, you're going to start realizing that you got a whole complete page of a lot of identities, and you're going to start feeling threatened now about whether you have to memorize all of these. But a lot of these, see, there's the algebra that help you derive one right from another. See what I mean? And everything is really just all of these guys right here, including these fancy ones, all built from that one. Right. So this version right here, we can rearrange that as tangent square equals secant square theta minus 1. Just rearrange that 1 to the other side. There are so many ways to write that. Now, what about on the non-unit circle? Right? We want to, because these mostly we focus on the unit circle. But then when you're on those circles that are non-unit circles, you got a different way of seeing it. But this is always true right here. Tangent theta is defined as sine of theta, right? Over cosine theta. You guys agree with me on that, okay? And then I mentioned that when you're when you're away from the unit circle, meaning you're on some circle with radius other than 1, some radius r. That's what I meant by non-unit circle. Okay. But your terminal point is always having coordinates x, y. And so now you already learned previously that hey, sine on any circle that's other than the unit circle, then sine is defined, right? It's understood as what? Y over the radius r, right? And that was just a few lectures ago, right? And then cosine was x over r. So that means what? It's a y over r times the reciprocal r over x, right? We cancel out the r here. We're ending up with y over x. So this gives us one formula. So aside from seeing tangent as a sine over cosine, it still is. But you can also see tangent as in case you have only the coordinates. Okay? In case you only have the coordinates, y over x right here. So when you're not working on a unit circle any longer, right? You can always take the coordinates, right? Y over x. That gets you the tangent value of your angle theta. So right now we are on the non-unit circle, right? And your terminal point, making that angle theta right here, your terminal point is at coordinates x, y. Right? Once again, please have your unit circle ready. So cotangent of theta, from our definition, it was cosine of theta over sine of theta. Right? And then cosine of theta further is from when we've learned earlier that when we're on the circle that's other than the unit circle, then cosine of theta is defined to be the x coordinates, right, but divided by the radius. So the x coordinates divided by the radius from where your point is, right, to the center of the circle. Okay. And then the same way the sine value on a non-unit circle is defined to be y over r. So in that way, we are reducing it down to algebraically x over r, the numerator, the fraction that's on the numerator, we multiply with the reciprocal of that fraction that was in the denominator. And so now canceling out the r over here, we're looking at x over y. Right? And so now we have come to another realization that anytime you have you have a point, right? A terminal point that stands at some coordinate x, y, then cotangent of theta can be found by simply doing x over y. Did we follow the algebra to get things done with that? Right. And so there are a few other ones that I want to mention. Secant of theta. By definition, I give out right there, it's 1 over cosine of theta. Right? We define secant as the reciprocal of cosine of theta. And so that just means, once again, when you're on a unit, when you're on a circle that's no longer the unit circle, and it's 1 over x over r. So everything I'm doing here is based on the familiar information that we've had. Sine of theta when you're on a non-unit circle, and sine of theta is y over r, and cosine of theta is x over r. That's why I've been using these into our work right here to derive these new relationships. And so, once again, this is the reciprocal of a fraction like this. So secant, that means secant of theta will come down to being as easy as just r, the radius, over x. Come to another one. Then, similarly, we have cosecant of theta. That was defined as 1 over sine of theta. That means algebraically it's 1 over sine of theta on a circle that's non-unit, right? That's not a unit circle, and it's y over the radius r. So we're looking at y over the radius r being put in that denominator. So now what it says here is that we're taking the reciprocal of y over r, so making it r over y. So we come to another connection right here, that cosine of theta, right, will always equal to r over y. I mean cosecant, not cosine. Okay, cosecant. Okay. Those are the new trig functions that we've learned with that. So now I'm going to bring in another example for you. Let's call it example 2. And of course, it's easy to calculate sine of theta and cosine of theta, but we don't need to do that anymore. So the picture is as following. Right now, I'm not even going to worry about the circle. You got a point being at 5, 10, somewhere like that. 5, 10, and that's our point. We call it P, right? So this point right here, like so, in what we've learned so far already, any point on the plane stays on some circle, right? Center at 0, the origin with that. Center at 0, 0, the origin, and make some radius. You guys with me on that? Yeah. Okay. And so that's the idea. There's always a circle that contains that point of yours. And then so from the standard position here, we're going to make some angle, and that's the angle theta. We've attempted to find tangent, right, and cotangent, and secant, and cosecant. Okay. So now, when you're looking at calculating tangent, you first may worry that, hey, do we have to find sine of theta? And then, because originally tangent was defined as sine of theta over cosine of theta, right? But in here, sine of theta is not immediately given, and cosine of theta is not immediately given. You may worry, and that's not the wrong way. I mean, you can also do calculating sine, calculating cosine, right, and then divide it out to get tangent. But that's not a good plan. It takes longer for us, especially in a problem like this. Nowhere in the problem it gives us a specific instruction about you gotta find sine and you gotta find cosine. See what I'm saying? Huh? So there's a much more direct. I'm talking about a direct route here. So we don't need to calculate sine of theta and cosine of theta. The tangent of theta, since we have a point, the terminal point, we're given x and y coordinates, right? That formula is directly given right here. And that's, we can just directly using it. Right? And so tangent of theta is given now as what? As simply y over x. See how direct that is now? We no longer have to use a sine and cosine, even though you could, right? If you were to spend your time doing that. So here, y value was what? It's 10. So we're looking at 10 divided by 5, right? And so the tangent value comes out being positive 2. And we found that value right there. And so now similarly, once you got a hang of that, right? From where we're going from here, where we're going next, cotangent of theta. Once again, as a strict definition, cotangent is cosine over sine, right? But in this problem right here, we can actually skip finding cosine and sine. We can just directly get into calculating cotangent by simply relying on that formula right here. We got x over y since the two coordinates values are immediately provided already. Okay? So we have 5 for x over 10, right? Let me repeat the formula one more time. We've got x over y, right? And that's x is 5 in this case, y is 10, right? So we're looking at cotangent of theta is 1/2. All right, and then so in that way we can also calculate secant of theta and cosecant of theta without calculating cosine and without calculating sine. But what's waiting for us here is we need to figure out on this circle, and definitely it's not a unit circle, right? On this circle, how big is the radius? We need to figure that out. Because the unit circle is always radius 1, so by default we don't need to worry about the radius. But now we're on a circle that's not necessarily a unit circle, right? So you need to figure out how big, how large that radius is. You guys will get that still? So before I get into secant, right? This famous formula again to calculate the radius from the origin out to any point. You go x squared plus y squared, right? In the square roots, that will equal radius. Remember that formula we given out a little while ago? The radius, right, from any point, coordinates x, y, from the origin to that point x, y, the radius is x squared plus y squared inside the square root. That's how we get the radius. So in that case, in our case right here, the point is at 5 for x, so we got 5 squared, and 10 for y, so we got plus 10 squared. Yeah? Take all that sum in the square root. So whatever the calculation here will give us the square root. I highly recommend using just the exact square root expression with that. So in this case, what do we have here? That's making 100, right? That's 25, so it's the square root of 125. Good with that still. And then you can reduce this square root as a 5 times square root of 5. Right? As a reminder, 125 is a 25 times 5. You guys recall that? Okay. And so taking the square root means with the square root property, we can break that as a square root of 25 times the square root of 5. So this guy is irreducible, and this guy here is a perfect square, right? So you can reduce that down to the square root of 25 is a 5 square root of 5. That's how I write that. Okay. That's just a quick little scratch word for everyone. So now that we got the radius, which is beneficial for us for calculating secant, and further on, when we're calculating cosecant, we're gonna have to also utilize that information. So it's a good point here that we're calculating the radius. Now I'm going to swing to the other board. Okay. So now secant of theta has to be in theta is this opening up of the angle. Okay. Now we're looking at r is being 5, square root of 5, and we're dividing that by x, right? The x coordinates. So now that's simply, and we can reduce that fraction by the common factor of 5 like that, so it's reduced down to square root of 5. So secant of theta in this problem right here. So what it says is for this terminal point sitting at 5, 10, right? After knowing that it made some angle in standard position with the x-axis, then secant of that angle, right? Secant of that angle over here is a square root of 5. That's it. And then so last one right here in the problem, it was asking for cosecant. Okay, so cosecant of theta. It's better to put those in parentheses. Right. Now we have r, the radius, square root of 5 over 5, but we're dividing that by 10, right? The y value with that. Right? It's just a matter of applying the straightforward formula. So we got the square root of 5 over 2. Because the 5 cancel with 10, right? 5 cancel with 10, gives me a 2 here. That's how it happens. So we found those values again. So that is one example that shows the direct application of how we can use the identities. I mean, these relationships between cotangent, tangent, sine, secant, and cosecant when you're on a non-unit circle, right? When you have a point with given coordinates. Okay. So, in the earlier lecture, I also mentioned we already reached a few identities, right? Quite important identities that shows the permanently true relationships. So now let me remind you guys some of those. Those that we already been through. So yes, it's all started out with yes, sine square of theta plus cosine square of theta must always equal 1. Thank you. Okay, so from that fundamental one that we have, just right from there, then we can go cosine square can equal to 1 minus what? Minus sine square of theta, right? So we've got a few of these important ones. And then the same one right here, we can go sine square, right? We equals simply 1 minus cosine square. Another version. So these are just the rearranged version. That is that one. Okay. And then we also did a little bit of deriving order for that, right? And so we came out with 1 plus tangent squared, right? That equals to secant square of theta. We learned this in the previous lecture. It was derived right from that fundamental one again. Okay. So those are the identities. And so from that identities, we can come up with. We can also lead to having tangent squared, right? Theta will equals to secant square of theta minus 1, sort of like the rearranged version of that one. Okay. Like these two are the rearranged version of that fundamental one. And then this one here is a rearranged version, like bring the terms around to different sides of the equation, that's all, right? And then from that fundamental, we show the work, we discovered that it was also 1 plus cotangent square, right? Theta will equals to this cosecant square theta. Remember the deriving work, and we spent some time doing that in the earlier lecture. And then we also have a rearranged version. You can go about cotangent square, right? Equals cosecant square theta minus 1. Another rearranged version of that. That's enough for reminders, right? So these are the identities. So now I'm going to bring in a few examples where you guys can learn how we can apply and how to use these identities here. So let me now call it example 3. Because it's straightforward. We can directly use these identities like this. So in this example, allow me to lead the way for you guys to see how we can use these identities here. Now, it's actually similar to some of the apply example we've done in class earlier right now as well. So here's how I'm doing it. You see right here, we got tangent theta given, right? And we don't know sine of theta. We only know that, hey, sine of the angle theta is a positive value. And we don't even have to know what angle theta that is. But here's the thing. We know from the identities that 1 plus tangent square theta must always equal to what? Still right in front of you. Secant square, right? You guys agree? It's a well-known, right, proven result here. Now, so in the role of this identity, now tangent is given to be a 3/2. Right? So I'm going to substitute that 3/2. And by the way, I've been introducing the square notation, right? This means what? The tangent value being squared. So in this expression right here, I'm talking about 1 plus. Now I'm substituting tangent by 3/2. So the equation becomes 1 plus 3/2 all squared, right? And that equals secant square of theta. You guys follow my explanation? 3/2 all squared plus 1 will equal secant squared. And it all came out because of this famously known identity we wrote on the board here. Okay. And so now, let's go ahead and do some math right here. So it's 3/2 all squared is a 9/4, right? So 9/4 plus 1 secant squared. 1 plus 9/4. Go ahead and add it up and give that in fraction right there. 13/4. Right? So that means now, on the other hand, in my next step, we have 13 over 4 equals, now remember that secant is 1 over cosine, right? Secant is 1 over cosine as a reminder. So now the right hand side here will become, so we got 13 over 4 equals 1 over cosine square of theta. There's a secant square on the right hand side, right? Secant square of theta on the right hand side. So the right hand side now will become 1 over cosine square. So why do I want to turn that into cosine square? Because, see, look ahead a little bit, right? The ultimate goal here is to calculate the value of cosine. See what I'm saying? No? So we brought our way down to something that displays cosine, right? So we're getting closer. And so now, but it's right now, it's the reciprocal of cosine squared. So we want to take the reciprocal of both sides of our equation. So we're going to make that, and I'm going to swap the order of the equation a little bit. So now we've got cosine squared, right? Reciprocating the cosine, I mean the secant. And now we've got 4 over 13. Are we good? Now we see a way to find out the value for cosine, right? Cosine is simply found by taking the square root of both sides. But now taking the square roots, anytime taking the square roots, we're always going to end up with 2 separate answers, right? A plus and a minus. So square root of 4 over 13, like that. Right? You got 2 answers. You got 2 answers. Plus and minus right after we're taking square root. So which one is the right choice for us? The positive would now allow me to jump in and explain a little bit about how we choose a positive one. Okay? So I heard suggestion to choose cosine theta to be the positive one. Okay? But think about it. How do we choose this? How do we know to choose this information? So now we look back. Okay? Putting question mark right here. We're looking back at that information. So we have utilized this information for tangent, right? Equals we have, and we use the identity that we learned, right, to come up this far right here. We ended up with 2 separate values, positive and negative, for cosine. This one piece of information we didn't pay attention to that until now. See, sine of theta given to be positive. It means what? Think about the unit circle, or just any circle. It doesn't have to be unit circle, but sine of theta is always related to the vertical coordinates. You guys follow it? Sine of theta is always related to the vertical coordinates. I mean, if we are on a unit circle, then it's exactly the vertical coordinates, right? If we're on a non-unit circle, then it's the vertical coordinates divided by r, right? And r is always positive. See what I'm saying? Huh? And so now we're saying a sine of theta being positive. That means what? The angle has to be either quadrant 1 or quadrant 2. You guys will be on that, okay? Right? Quadrant 1 or quadrant 2, right? Sine is positive. We have the whole upper half circle over here. But yes, I forgot. But now with that information of tangent itself, right? Given as we have here, yes, it's a positive. Yeah, so combining that. Because there's no way it's in this second quadrant. See what I mean? Because it being in that second quadrant and the cosine is being negative, right? And then cosine being negative, it's going to make the tangent negative. So we don't want that. So with this information, together with the sine theta being positive, like that, yeah, so it leads us down to the only way it's another way of saying that we're in quadrant 1 right there. That's the information. Okay. Right? So being in quadrant 1, yes, it leads to having the positive answer here. That's now how we have that answer decided. You know what I mean? So sometimes the information about the quadrant can be given directly, but in this problem it's tricky a little bit in the sense that it gives you the sine theta value, right? And then we combine it with the tangent theta information like that. I mean, once it's given, you should also know the sine of your tangent, right? All right, so that's how we're doing a problem like that. And then think about the impact right here. Once you found cosine, right? Once you found the value for cosine, you should be able, even though the problem here didn't ask for it, but think about it as a consequence or as the impact right here. That's the impact. You should be able to also calculate sine of theta. See what I mean? Because once you've had the cosine of theta, right, then you can go sine squared of theta will always equals 1 minus cosine squared of theta. See that identity that we've had on the other side right there? And then throw that in there, right? Square that value right there. And then you're going to have sine squared of theta, right, will equals 1 minus and all of that, the square root of 4 minus 13, right? And the square is going to cancel out the square root, and you should be able to calculate the sine squared, and we take square root, right? And then once you got sine and you already calculated cosine, right? You should be able to calculate as an impact, even though the problem didn't ask for it. You should be able to calculate. You should be able to calculate the cotangent easily by doing cosine over sine. And then you should be able to calculate, and the secant is quite straightforward right from the earlier steps already. And then you should be able to calculate the cosecant, right? Right out of that by doing 1 over sine. And so the problem, even though it didn't immediately ask for those, right? But we can easily think about, after tangent, we can calculate cosine, and then from there you can calculate sine, right? And all of those other ones easily. So there could be problems around among your assignments where it's asking, hey, you got tangent given, or you got some of the cotangent given, right? And then you use the identity over here to find one of the other major trig functions, and then from there you can calculate the value of the rest. Right? And that's the idea of this example right there. Right? Let me call that example 4. Give you guys another shot at about. Let's just evaluate, right? So it's a trig expression. And then right now we want to be now. Anyone would like to pick an angle theta for me? Use the one that comes right out from your unit circle in radians. Go ahead, look in your unit circle and pick for me one angle that you prefer. So how about given theta equals 5 over 6, right? Let's go ahead and evaluate this expression right here. So it's just for us to get comfortable with calculating this. And so basically it just means we're substituting 5 or 6 in places of the angle theta. Right? We were looking at tangent square of 5 or 6, right? Added to sine square of 5 over 6. So that one right here, just write it down here. It's a 1/2, right? But then we're not just only doing 1/2, we're doing what? 1/2 all square. Right? See what I mean? Okay. So what about tangent? Tangent gotta be what? Sine of 5 over 6, right? Over cosine of 5 over 6. See what I mean? Okay. And then you're gonna square whatever that answer is, and then we're gonna add. But then we already knew from what we have done earlier, sine of 5 over 6 is 1/2. So here we've got a 1/2, right? So the only missing information is what about the cosine of 5 over 6? Okay. I'm still waiting for cosine of 5 over 6. Okay.
Square 3 over 2.
Okay, put 3 over 2. I like that. Putting that in here. Put 3 over 2. Okay. We need to square all of that. You guys agree on that? Okay? Do you all agree with those values that are given to me? So that now means, as far as the expression we're looking at, so inside a big square right here, we got a fraction over a fraction. Okay, so that's a 1/2, and multiply with a 2 over square root of 3 with that. Okay, and then we square that. I'm holding on to these squares a little bit. The last step right here. So now that cancels out the 2 inside the square. Right? We're looking at the 1 over cube root. Square root of 3 all square plus a 1/2 all square. Okay? And that will give me simply enough. So now squaring that is going to make me just a 1/3, right? Plus a 1/4. You guys all good? Right. Simply major common denominator, right? By multiplying these two relatively prime factors. We've got a 7/12. Yes, so that's the way how we do that, right? So I just want to make sure that you guys watch out for the order of operation right here. So we think of the tangent right here as a sine over cosine, right? And then we substitute in the 5 over 6 into the angle right there, right? And then so forth. For each of these, so the best way is to bring all of these. So sometimes when you have like those other than the sine and cosine, bring it down to the expression that involves sine over cosine. And then at that, we're we can easily calculate the value. And then that's just one way of how I do it. For safety of the work, then you can also directly calculate tangent of pi over 6 as well. That shouldn't be too too important. Sine of theta plus cosine of theta. That to be 5 pi over 3 pi. And then, yes, it's just to demonstrate the purpose and to keep class going easily and smoothly. So a lot of times I stay with those common angles from the unit circle. But there could be times where you can stay with some angles that aside, outside of those are common angles as well, right? Because there are other angles on the unit circle that we never really looked at. And then when we calculating those angles aside from these common angles, then you're gonna have to use a calculator for that, right? And make sure you turn your calculator in degrees. In radians. But then a lot of times we just stay with these common angles on the unit circle. So the 5 pi over 3, when the theta is given to be 5 pi over 3, then we're looking at substituting in sine of 5 pi over 3 plus cosine of 5 pi over 3, right? Square 3, you say negative?
Yeah.
Square 3 over 2, right? What about the cosine? 1/2. I'm going to just simply add the two, and they already have a common denominator, right? So your fraction here becomes the exact expression over 2, but what we have is 1 minus square 3 on top. That's the added. Part C, how about cosine square of theta minus sine of theta times cosine of theta. So the expression here is already in terms of just strictly sine and cosine, right? So not much to worry about. We got cosine square and substituting in theta by 3 pi over 4. Okay. We're substituting sine of 3 pi over 4, and then we multiply that with cosine of 3 pi over 4. So just substituting in the order of the steps here, just substituting values in for the theta, right? And we're going to start collecting these values again. So it just means that we calculate the square after we got the cosine value of 3 pi over 4, right? So what's cosine of 3 pi over 4, by the way? 2, that's right. And then here say cosine squared, right? We're going to square that. And we subtract. So we put 2 over 2. And then the cosine of 3 pi over 2 we already found. Negative 2 over 2. Here I'm showing the steps just to make sure you guys understand the order of operations, but please, the way I'm doing here is not necessarily the only way, okay? You can have many other ways of doing it. See what I'm saying? No, but make sure your final answer gets in the exact expression. Yeah. Okay. So now the square of that gives me a 1/2, right? Positive 1/2, and minus. Now, actually minus, but then that minus making it a plus, right? And then the square root 2 over 2 times another square root 2 over 2, making it a 1/2 again, right? So our final answer comes out being what? 1. But it's not always 1, right? It's only 1 when the angle was given as a 3 pi over 4. The other angle, it may turn out differently. You know what I mean?